Okay, yes, now Wolfgang again, Embedded World 2016, last day of this fair, so 3 days here. We have the pleasure now to make a short interview with Trevor. Trevor is from company Pico from England, UK. So Trevor, what is your company history? So you are in Cambridge, where the university is the famous one, yeah?
We're very close to the... we're in the Cambridgeshire area, so we're very close to Cambridge, and we do take advantage of some of the benefits of the technology development that go on in that area. So,
okay, special technology here. We are talking about measurement technology. Of course, the fair is Embedded World, but as you know, microprocessors and digital communication, the signals are getting faster and faster, and how to measure, how to improve quality. I think it's a clever concept. Pico is focused on oscilloscopes, but not within a big housing. You can use a notebook typically and connect, for example, Pico 2000 series oscilloscopes just to the USB port. Is that right?
Yeah, that's right. They're blue, and we call them picoscopes. So that's the name of our product. So they are PC connected, and the connection is through a USB interface at the back of the instrument to a host computer. In some cases, like the one that you mentioned, the Picoscope 2000, it is not only the communication from the scope to the laptop, but also the power. So the power is provided by the host computer to drive the Picoscope. And then we have a range of Picoscopes with either 2 channels or some models with 4 channels. So we have the 2000 series that you mentioned already. We have the 3000 series, which are a little larger with deeper memory, still connected to the host computer with a USB interface. But then we have a choice of either 2 or 4 channels, and in fact, in the example that we're seeing here, 4 channels plus 16 digital channels. So 4 analog channels, 16 digital channels that connect to the device under test here with a group of connectors here.
Yeah, I think it's important to understand a little bit what is the typical purpose, what to measure. Of course, when you talk about cellular communication, mobile phones, then digital has to be approved that the quality is good, for example, or for testing environment, for developers, it's very important to have such measurement technology. And I think is a good alternative to a classical oscilloscope. Why?
Well, one of the things that we're really working very hard on is to help engineers who are working on serial buses. So serial buses in all sorts of systems, in embedded systems, in automotive, in telecommunication, in medical electronics. Serial buses such as I2C, SPI, CAN, LIN in automotive applications. Those serial buses are being used extensively in all sorts of embedded systems. So when they work, they're great. It's a really much better idea to have a system that's using a serial bus than the older generation parallel bus. But during the design process and the product verification process, if things go wrong with a serial bus, you need some help. You need some tools so that you can dig a little deeper to see what's going on. So we currently have support for 16 serial protocols so that we can decode those protocols. And the idea then is that through the decoder, you can see, and it's actually I'll just switch it on. So what we're seeing here on the screen here is an I2C stream. We've got the clock and the data, and if I turn on the decoder here, we then start to see what is happening in terms of the data in each one of those packets. So if we expand this a little bit, we can see the details of the address and the data and any errors that are reported. We can see those in a color coordinated way, so that visually it's very easy to identify where there are errors in the data. Now that's the first step, but the important thing beyond that is once you've seen an error, what is the cause of the error. So the idea of having a serial decoder and on a picoscope is to enable that ability to find the error, see what the error is, and then look for the cause of the error, which normally is some sort of signal integrity problem. It might be some crosstalk or some noise or some other timing issue that exists in the waveform, and that correlation really is the ability to correlate that is huge help. It's the tool that the design engineers need to debug their designs.
Okay, very interesting. I think some key features. I think measurement technology has to be very fast, very accurate, reliable. Software is something very important, as we see here, and decoding is some intelligence. Let's say how to detect. Maybe you just see the device is not working or your development, but you don't know why. So to find out, maybe the signal or the error occurs somewhere. It's hidden. Yeah, you are as blind, you cannot see anything. And I think triggering is also very important. Is that right?
Yes, it is indeed. So we have a range of triggers so that you can try and home in, try and isolate just those error conditions. So trigger conditions such as pulse width triggering, less than, more than, or equal to a particular pulse width that would, in a system, may represent an error. We have what is called runt pulse triggering. So normally in a digital system, a pulse should swing from low to high completely. If a pulse starts to go high and then doesn't quite make it and turns low again, it's probably an indication of a setup and hold time violation. And having those triggers, we can trigger on those error conditions to very quickly find the signal integrity problems that are so important to resolve before a product goes into production.
Very important. So during development, of course, if the product is ready, it shouldn't occur. But also in this case, maybe for maintenance, it's also important to have a laboratory equipped with very good measurement technology. So Picoscope could be really interesting for everybody who is developer. And okay, there are different series. The difference is, I think, it starts quite easy. Maybe it's not so fast. So sampling rate is something important, I have heard, and also the bandwidth is very important. So the key features. Can you explain shortly bandwidth? What we can imagine, or if maybe somebody is not so familiar with that term, could you explain a little bit?
Well, it's quite a complicated topic, but we'll just to explain it in brief. What an engineer should do is to choose much more bandwidth than the maximum bandwidth of the signal that they're trying to test. So if you're trying to measure a 10 megahertz signal, it's a good idea to choose 100 megahertz bandwidth oscilloscope in order to have a good representation of the waveform, so that the waveform that appears on the screen is a good representation of what is really happening on the device under test. So bandwidth is analog bandwidth is one important characteristic to keep in mind. Sampling speed, you mentioned, is another one. So sampling speed is the speed of the analog to digital converter, and the faster the analog to digital converter, the better the oscilloscope is at looking at those small glitches or random anomalies that can cause so much trouble in a digital design. So high bandwidth and high sampling speed, more is better in general.
More is better than this typical in life, but also in technology. So, but I think another problem is you have to do a compromise. So if somebody has the intention now, and I hope so, that picoscopes are sold now very frequently to all of you listening to this interview now, because it's really something very strong and unique. Notebook has everybody, computers, but a strong and reliable measurement technology is really something very important. But the difference is also sampling a lot of data and has to you have to have a huge memory. But if you have a huge amount of data, it cannot be fast in the same time. So do you have to find the right compromise about what you need? Is it right?
A compromise, but also clever design. So both of those things come into play. So several of the picoscopes that we have, the 3000 series, the 3000D series here, for example, it has a memory depth of up to 512 megasamples. So it's a huge amount of memory. It's divided across the number of active channels that you're using, but it's still a massive amount of memory. So, of course, we've got all of that memory in the box. If we were trying with every acquisition from the oscilloscope, if we needed, even with the USB 3 interface that we have here, if we were trying to get all of that memory to the host computer, each trigger event, it would slow the system down a lot. So what we do, here's the clever engineering bit, is that the FPGA inside the picoscope, it collects the data and it figures out from the software that's running on the PC, it figures out what is the minimum amount of data that needs to be sent back to the host computer in order to achieve not a slow but actually a very fast update speed on the screen. So you get a really rapid refresh speed. It depends a little bit on the performance of the host computer and of course on the model that you choose, but the USB 3 models that we have here, we're achieving waveform capture rates of up to 130,000 times a second. So it's it takes a lot of engineering, but it does deliver then really high performance, so that you get visually a good representation of what's going on when parameters change.
Yeah, Pico is not a new company on the market. They are really experienced. So you see all these guys here working, typical engineers. I think it's very special. Could you show some product or maybe show us a measurement typically, or some special new things here on this fair here on Embedded World?
So actually, before I will do that, but I'd like to just say one other thing. You mentioned that Pico is not a new company, and it's true. Actually, on June or July the 2nd this year, we will celebrate our 25th anniversary. It's 25 years since the company was founded. So
almost congratulations, but not.
It's getting close. So yes, so as one example, so we looked already at the example of decoding of serial data. So that is an important application that we address with the picoscopes. Another interesting one, I haven't particularly got a signal set up to show it here, but I can give an example, is that we have the ability to plot frequency against time. So normally on an oscilloscope you have a time domain shown in the x-axis, amplitude in volts displayed in the y-axis. So that's normal for any oscilloscope. But what we can do is through the math channels here is create an advanced math channel, and we can say, right, let's plot frequency of channel A, for example, against time. And then it says, okay, what color do you want that to appear in? So black seems to be fine.
Color selection is the easiest one here, but
and then a few other parameters about how we want that to be scaled, and then next, and then finish. And what we will get, now I haven't really got a suitable signal set up there for that particular measurement, but nevertheless, then if you're looking for changes, subtle changes in frequency or dramatic changes in frequency across the deep memory waveform that you've captured using those 512 megasamples in the 3000 series here, you can plot that as a trace on the screen. And it's really useful if you're trying to look at the performance of a phase lock loop, or you're looking at frequency shift keying of the modulation of a RF signal, something like that. So these are advanced waveform processing capabilities that you need deep memory for, and give engineers more insight into the operation of their designs.
Very good. Thank you very much. I think it's for a first impression. You can ask many questions, of course. If you have time, come here on Embedded World here and ask questions directly to the Pico guys. They are really experts. I would say techies, typically. The techie here is. So use the time. If you have no time to come here on the fair, you can ask through the community, of course. We will forward the question to Trevor and his colleagues. And of course, Konrad is a distribution channel for Pico products, so Pico Scope. Ask us as well. I wish you a successful fair. Thank you very much. It was a pleasure to talk to you.
It's a pleasure to talk to you too. Thank you for seeing us.
Thank you.